Hi guys, this is Mr. Mellor. This is a video to help you get through the worksheet of part 3 of our project. Understanding that this part 3 is going to be due next Monday, and part 4, which is actually designing your final bridge, is due next Friday, which would be 11/20. Okay, so let's go ahead and get started. The learning objectives, of course, are to learn about equilibrium as it applies to bridges. We're going to practice solving equilibrium problems, but I want to stress that you have the choice of choosing to design a truss bridge or suspension bridge in Tinkercad. I made a video to do both of them, so you can choose if you'd rather work on a truss bridge for this one because you think maybe your final design would be more similar to that, or if you want to make it a suspension bridge because you think those are pretty cool, you can follow along and see how I did it in one of my 2 videos. All right, but the purpose of this particular video is to help you with the questions. So first part is to verify your bridge design. When you have your final part of your project, again, due next Friday, it's going to have a table very similar to this. And so some of us haven't been filling this out properly. Basically, after you've designed your CAD model by following along, we're just checking, is the length of the bridge actually 8 inches? Yes. Is the height of the legs 2.5 inches? Yes. Is our height of our bridge overall less than the maximum height 7 inches? Yes. Required width 3 inches, certainly, and the thickness of the deck 1/16 of an inch. All right, so let's get into these problems in particular, though. What we have is we did these in class, and so remember that the goal of bridge design, so our goal is to make sure we're always in mechanical equilibrium. And so what does that mean? Well, equilibrium is when the sum of our forces is equal to 0. Okay, and so in this case, we have 1,000 newtons down, we have 500 newtons upwards. So what must F1 be to make sure that we have 1,000 newtons up and 1,000 newtons down? Well, we know that the sum of the forces are equal to 500 newtons up plus F1 minus 1,000 newtons. And for us to be in equilibrium, that has to be equal to 0. So F1 must be equal to 1,000 newtons minus 500. And so our answer should be 500. Okay, it says highlight our answer. So of course we're going to follow the rules and highlight. All right, so next question. What is the value, and this is a truss bridge, what is the value of the vertical component of F1 and F2, F2 in particular, in the image above that would keep the bridge in equilibrium and therefore keep it from collapsing? All right, so think back to projectile motion. In projectile motion, we said that all diagonal arrows we can actually break up into a vertical component and a horizontal component. And so the same is true with forces. We can break up our diagonal forces here into a vertical component, F2 vertical, and we can break it up into a horizontal component. And so diagonals are particularly useful because not only with this diagonal truss member can we oppose a vertical force downwards, but we could also oppose a horizontal force. Okay, and so in this case, what we have is we have 800 newtons upwards. 800 newtons upwards already. We have 1,500 down. And then we also have our F2 vertical, and that has to equal 0. Okay, so we're going to go ahead and solve that. I think that you guys can solve this equation here to get our answer. Okay, so what is F2 vertical? It is the force that our bridge needs to support from this leg, from this beam, such that the sum of our forces add up to 0 and our bridge is in equilibrium. Okay, next question, we have a suspension bridge. Well, remember, the purpose of suspension cables is to make sure that no matter where we are on the bridge, no matter where our cars are located, we're always in equilibrium. And so we're going to see with these problems is we're doing exactly that. If our load is in the center of our bridge, then we have our suspension cables are quite literally picking up the slack. And so we get the net force is equal to 4 times the tension in the suspension cables. In this case, they're all equal. minus the weight that's on the bridge, 1,200 newtons. That's equal to the mass of the bridge times the acceleration of the bridge. And since we're in equilibrium, it's equal to 0. Since in equilibrium. Okay, and so the question is, what is the value of F if we are in equilibrium? Well, that simply becomes F is equal to 1,200 newtons divided by 4. So you guys can solve what does that equal for our answer. All right, if we look at our bridge slightly differently, now if we have our tension here had been supporting our weight, well, if we take a look at it from the point of view of the overarching rope, now we have that tension is being reacted upon, and so we have 4 red weights down, and so those red weights are all adding up to that same 1,200 newtons, and so the overarching cable needs to be able to support that, and that's F1 and F2. So our overall vertical sum of forces is the vertical component of F1 and F2, which in this case are equal, minus the weight that's being supported by these 4 tension cables, and that's equal to the mass of our bridge times the acceleration of the bridge, which is 0. So now we just need to solve F1 and F2 are equal to 1,200 newtons divided by 2, okay? So we see we just took this equation and we solved for our unknowns, which is F1, F2. That's these forces, the vertical components of those forces right here. Because remember, again, the goal of good bridge design is to make sure that we're always in equilibrium. The sum of our forces always adds up to 0. All right, and the based on the diagram above, so that one we just did. Question 6, what should the value of F be to make sure that the bridge is in mechanical equilibrium? This is the same problem, so I'm going to let you guys do this one, okay? Same problem as above. All you need to do is determine, based on this equation, what should the value of F be such that we're always in equilibrium. The sum of our forces always adds up to 0. All right, what are the pros and cons of a truss bridge design? Okay, so this is in the truss bridge video, so you guys can look there. And then finally, question 8, start your own design. How exciting. So this is part 3 of our project, part 4, which is due next Friday, remember? Not this Friday, Friday the 20th before Thanksgiving. You're making your own bridge design in Tinkercad, so draw a design of what you would like your final bridge to be. I'll go ahead and make one right now. This is as simple as you just need to make it, your own. So don't copy what I'm putting right here. So I'm going to start off by showing a basic beam bridge. Then I'm going to go ahead and add some trusses. Okay, and then I think that I'm going to do an arch at the bottom. Okay, so my overall design is going to be, at least preliminarily, this is what I'm thinking, a truss bridge with an arch. Okay, all right, and that's all you have to do for this portion of the project. Next part, you will be implementing your design, and there will be specific requirements for you to work on. So looking forward to seeing what you do, and I'll see you guys in class. Okay, bye guys.